topic 4, waves. 4.1 Oscillations. Oscillations are vibrations which repeats themselves. Oscillations can be driven externally like a pendulum in a gravitational field, like this. Oscillations can be driven internally like a mass on a spring. In all oscillations, velocity equals to 0 at the extreme points. But you can see velocity is 0 at extreme points. And velocity equals to max in the middle of the motion or in the equilibrium positions. You can see in the equilibrium positions, velocity is maximum. Oscillations can be very rapid vibrations, such as in the plucked guitar string or tuning fork. Consider mass on a spring that is displaced 4 meters to the right and then released. We call the maximum displacement XO the amplitude. In this example, the amplitude is 4 meters. We call the point of zero displacement the equilibrium position. Displacement x is measured from the equilibrium. The period t is the time it takes for the mass to make one oscillation or cycle. For this particular oscillation, the period t is about 9.78 seconds. So let's see. Start, quarter, half, 3/4, and complete oscillations. Time period and frequency. Frequency f measured in hertz or cycle per second is defined as how many cycles, oscillations occurred each second, or frequency is number of complete oscillation per second. Since the period is second per cycle, frequency must be 1 over t. So frequency equals to 1 over period, or period is 1 over frequency. Let's take a look at this example. The cycle of previous example repeated each 9.78 seconds. What are the period and the frequency of the oscillation? So the period is t equals to 9.78 seconds. Frequency f equals to 1 over t, which is equals to 1 over 9.78. That gives us 0.1 hertz. Phase difference, we can pull the mass to the right and then release it to begin its motion. Or we could push it to the left and release it, like this. Both motion would have the same value for period and frequency. So first one is start stretched, second one start compressed, with the same period and frequency. However, the resulting motion will have the phase difference of a half a cycle, or 180 degrees. So two motion are half a cycle out of phase, or phase difference of 180 degrees. Two identical mass spring systems are started in two different ways. What is their phase difference? Let's take a look at. Start stretch it and then released. Start and stretch it with a push to the left. The phase difference is 1/4 of a cycle. You can see phase difference is 1/4, which is a phase difference of 90 degrees. And 90 degrees pi over 2 radian. The two identical mass spring systems are stretched two different ways, what is their phase difference? But a slightly different way. Start stretched and then released. Start and stretch it with a push to the right. Then take a look at the phase difference. The phase difference is 3/4 of the cycle. 1/4, 2/4, 3/4. So the phase difference is 270 degree. So the phase difference is 90 degree, 180 degree, and 270 degree, or phase difference in 3/4 of the cycle, which is 270 degree. Spring having a spring constant of 125 Newton per meter, which is spring constant, is attached to a 5 kilogram mass, stretched 4 meter as shown, and then released from rest. Using Hooke's law shows that acceleration A of a mass spring system is related to spring's displacement x by the proportion A proportional to displacement. We look at x component. Only force acting on x component is spring force, and ignoring drag forces. So the net force equals to F equal to minus kx. Spring force and the displacement are opposite direction. The minus sign indicates direction. And we also from Newton's second law that F equals to ma. And only net force acting on it is spring force. So we equate these two equations. ma equals to minus kx and a equals to minus k over m times x. K is constant, mass is constant, so acceleration is proportional to minus x, or acceleration is proportional to displacement but opposite direction. B. Tailor your equation to this example and find acceleration of the mass when displacement equals to minus 2 meter. C. What is the displacement of the mass when the acceleration is minus 42? So based on our derivation, A equals to minus k over m times x. That is minus spring constant 125 divided by mass 5 times displacement. That gives us minus 25 times displacement x. And we get acceleration equals to minus 25x. So when displacement equals to minus 2, we get 50 meter per second per second. C. We have x equals to minus 25x. So now acceleration is minus 42. Then displacement equals to minus 42 divided by minus 25. So that is equals to plus 1.7 meter. From here we can see acceleration is proportional to displacement. When displacement negative, acceleration is positive. When acceleration is negative, displacement is positive, the opposite direction. So in simple harmonic motion, acceleration and displacement are related in a very precise way, namely A proportional to displacement and opposite direction. This is defining equation for simple harmonic motion. If any motion is behave in this way, acceleration proportional to displacement in opposite direction, that is definitely a simple harmonic motion. Shows that mass oscillating on a spring executes simple harmonic motion. We already derived A equals to minus k over m times x. K is constant, mass is constant, therefore acceleration is proportional to displacement in opposite direction. So this is definitely a simple harmonic motion. So let's take a look at the direction. The minus sign in Hooke's law, F equals to minus kx, tells that if the displacement x is positive, then a spring force F is negative. Let's take a look at. So the displacement x is positive to the right, but the spring force is pulling in opposite direction, which is negative, left. You can see the displacement x is towards the positive direction, or it's oscillating towards the right. Spring force F is negative and pulling it to left direction. So F and X oppose each other. It also tells us that if the displacement X is negative, spring force F is positive. We can see that load is moving to the left and the spring force is opposed to the right. Any force that proportional to opposite of a displacement is called restoring force. For any restoring force, F proportional to X displacement but opposite direction. And since F equals to ma, we see that ma proportional to minus x, or acceleration proportional to displacement but opposite direction. All restoring force can drive simple harmonic motion. Here's a very interesting illustration. If we place a pen on oscillating mass and pull a piece of paper at a constant speed past the pen, we trace out the displacement versus time graph of simple harmonic motion. So and we have a displacement time graph. A simple harmonic motion traces out perfect sinusoidal waveform. It can be a sine, can be cosine. In our particular case, it's cosine. The period can be found from the graph here, from trough to trough, or from here to here. Consider the pendulum to the right, which is placed in a position and held there. Let the green rectangle represent the potential energy of the system, and let the red rectangle represent the kinetic energy of the system. Because there is no motion yet, there is no kinetic energy, but if we release it, the kinetic energy will grow as the potential energy diminishes, like this. And a continuous exchange between kinetic and potential energy occurs. You can see at the extreme points, it's completely gravitational potential energy. At equilibrium position, it is completely kinetic energy. Maximum gravitational potential energy happens at the extreme point, and maximum kinetic energy happens at the equilibrium positions. Consider the mass spring system shown here. The mass is pulled to the right and held in place. Let the green rectangle represent the potential energy of the system. Here is elastic potential energy. Let the red rectangle represent the kinetic energy of the system. A continuous exchange between kinetic and elastic potential energy occurs. At the extreme points, we have maximum elastic potential energies. At the mean position or equilibrium position, we have maximum kinetic energy. If friction and drags are zero, then total energy is constant. Ek plus Ep equals to total energy, which is constant. If we plot both kinetic energy and potential energy versus time for either system, we would get the following graph. Green represents potential energy and red represents kinetic energy, and total energy is constant.